So last time we discussed the Tauberian theorem. Tauberian theorem. So, today we'll discuss, so we'll discuss equidistribution and applications of the Tauberian theorem. Okay. Now, I mentioned last time that there are sometimes elementary methods which are better in certain circumstances than the general analytic Tauberian theorem. So I want to, in that context, to discuss what is called Dirichlets' hyperbola method. We'll discuss the hyperbola method. And this method is very powerful, very elementary and very powerful. So as a kind of a motivating example, perhaps, let me ask you the following question. Let d of n be the number of divisors of n. Calculate summation d of n, find an asymptotic formula for that. And the naive way of proceeding would be to say, well, n is less than x, and I'm trying to count how many factorizations I have of n as a times b, and just count one for each factorization, right? This is the naive way of it. And then a times b is n, and n is less than x, therefore I can rewrite this as a summation up to x, and inside I'm actually counting n less than x, which are divisible by n, so a divides n, 1. And so this becomes x over a less than x. And when I try to remove the square brackets, I'm going to get x over a plus O of 1, right? And now you're going to get x times summation a less than x, 1 over a, plus O of x. And we saw by obel summation, partial summation, that summation 1 over a less than x, is equal to log x plus, well, I told you about this, plus this Euler's constant gamma, right? Plus O of 1 over x. Remember we did this, right? If you do it carefully, you get something like this. So you can try to plug that in. So here, if I plug it in, I get x log x plus gamma x. Plus gamma x is absorbed here, so it's irrelevant whether you keep gamma or not. So you end up getting x log x plus O of x by this approach. Okay, so which at least gives you the main term. I told you also last time how the Tauberian theorem can we used to handle double order poles and higher order poles. And when you use the Tauberian theorem in looking at this same thing, summation d of n over n to the s, n going from 1 to infinity, is zeta squared of s, and this has a double order pole, and so you would pick up x log x from that. Remember, every time for every pole, extra pole beyond 1, you pick up a log x. Okay, so you'll pick up this, and of course you won't pick up this error term. You'll just pick up an asymptotic formula from the Tauberian theorem. So at least this much, this naive elementary method is better than the Tauberian theorem in the context that you actually have an error term here. But Dirichlets observed that sometimes you can do better than this. It's a very useful method to have. So let me try to explain how this method works. General theorem is given by this Dirichlet hyperbola method. Suppose I have a function, or an arithmetical function, which is equal to d divides n, a sub d, or a of d, b of n over d. So supposing I can write my arithmetical function in this fashion, and let a of x be the partial sums of the a of n's, let b of x be the partial sums of the b's, okay, let's define these two partial sums. Then summation n less than x f of n is equal to summation d less than y a of d b of x over d plus d less than or equal to z b of d. If you don't mind, I'll just put e here. You'll see in a second why. Not that it matters. Minus a of y b of z for any choice of of y and z satisfying yz equal to x. So you have this very nice formula, and the proof of this fact is best given. So let me try to write the proof. We'll come back to this anyway. I need this board space. Let me try to write the proof actually as a picture. The picture. So here's the idea. So proof. Summation n less than x f of n is equal to summation d e less than or equal to x, a of d, b of e. Correct? I mean, f of n is, after all, a of d times b of e, as long as d is equal to n, and then n is less than x, therefore I'm doing this. This is the summation. Now, let's look at a picture. What am I doing? I'm looking at all pairs of natural numbers d and e such that the product is less than or equal to x. Okay, so let's draw a picture. And let's say this is the d-axis, and this is the e-axis. And the graph DE equals x is a hyperbola. That's where the name comes from, the hyperbola method. This is d equals x. And maybe x is up here, so this is an x here, and then e can go up to x also. So I'm basically looking at all lattice points. Of course, we don't include 0 because 0 is not a good choice, but all lattice points underneath here, underneath this hyperbola, I'm looking at, so I better not make too many lines here. Underneath this hyperbola, I'm looking at all the lattice points, right? That's what I'm looking. So I'm looking at each lattice point. A typical lattice point would be DE underneath that hyperbola, and I count A of D, B of E. Now, so that's for each lattice point, I calculate this thing, and I add them up for all those lattice points. Well, y times z is equal to x. Therefore, there is a certain particular point y, z on the curve, right? Y, z on the curve. And so in this calculation, all the lattice points with d less than y, all the lattice points with d less than y appear here, right, in this region. And all the lattice points with e less than z appear underneath here. Okay, so in doing this, I can do the following. I can say dE less than x, d is less than or equal to y. So these are all the lattice points with d less than y. And then dE less than x, e less than z. These are all the lattice points with e less than or equal to z. So all the lattice points with d less than or equal to y are in this region. All the lattice points with e less than or equal to z are in this bottom region. And there's this common thing that I've overcounted. What's the common thing? Well, d is less than y and e is less than z, so I have to remove that contribution, and you will see that that's just simply a of y, b of z. And when you work it out, this is what you get. Okay? So when d is less than y, I sum a of d, and then summation b of e, e less than x over y, x over d. So that's what you get. So when you work it out, you get exactly this. Very elementary idea, but as you will see in a second, it's very powerful. Now let's apply this. So I hope the proof is clear, right? You can fill in the details. Proof is pretty clear. Okay. Now let's apply this. I mean, I think it's better to do this with a picture rather than try and write it all out in words. As they say, a picture is worth 1,000 words, right? So, not a bad idea. Especially when you're doing contour integration, it's better to put the picture of the contour rather than say it verbally. All right. So, application. To the divisor function. So now what we will do is in trying to figure out n less than x, d of n, I understand from that thing that d of n is, of course, d divides n 1, the number of divisors of n. And so I can apply the hyperbola method with a of d equals 1, or a of n equals 1, identically 1, and b of n identically 1, right? We can apply the hyperbola method with that. And in that case, a of x is simply the greatest integer of x. And b of x is the same, of course. And so when I apply that, I'm going to get, first sum is d less than y of x over d plus e less than z x over e minus greatest integer of y times the greatest integer of z. Okay? All right. So you get this time. Now you'll remove the square brackets as before. So here, I'm going to remove the square brackets. Everybody okay with that? Now, at this stage, you should now examine, remember the constraint that is yz has to be always x. Okay? So if I pick y very small, I win here because the error term is going to be small. But then z is going to be big because it's got to be x over y. So the only way to balance this y and z here, there's an error term of y and there's an error term of z, and the product has to be x. Therefore, an optimal choice is root x for both of them. So we choose y equal to z equal to root x for both of them. That way you get an error term of root x here, an error term of root x here, okay? And here, root x times root x is an x, but then the cross terms give you an error term of root x. So this whole mess here turns out to be minus x plus O of root x. But you actually start gaining here. Let me rub this off because now that we're done with it. So what do you end up getting? You end up getting summation n less than x d of n equals, well, this time it's x times log y, log root x actually, rather, plus gamma plus O of 1 over x. Right? Remember that formula we had? Okay, okay. Oh, is it 1 over x or 1 over root x? D is less than or equal to root x now, so it's 1 over root x. Yeah. Thank you. And then the next term is x log root x plus a gamma plus O of 1 over root x minus x plus O of root x. Okay? So there's a half log x there, half x log x there, another half x log x there that combine to give me an x log x. Well, that we knew before. So at least the main term is coming out as before, which is not anything different. Okay? Then you have a gamma x here, another gamma x here, minus 1. This is the new element that you never had before. You managed to get the second term. And then the error term is, of course, O of root x. This is a very nice method. So this, for the divisor function, you get this nice thing, but the general principle is here. So anytime you can write your function f as some sort of Dirichlet convolution of two other functions, and if you know some information about these summatory functions, you can play this game and choose y z optimal. Sometimes it's helped. Usually, it's not always the case that the optimal choice is root x. It's not always the case. Sometimes it's, especially when something converges, there might be something different choices that can be made. So I'll let you play with that as a part of the your homework. Okay, so it's a very elementary, but you can start getting error terms. So now I might as well mention to you there's a major unsolved problem called the Dirichlet divisor problem. And the problem is, what is the error term? That's the unsolved problem. What is the error term? You have an error term here of x to the half. Conjecture is the error term is O of x to the theta for any theta bigger than a quarter. Now, one can show that theta equals a quarter doesn't work. These are called omega theorems in analytic number theory, okay? So, it is known theta equals a quarter is false. And I don't know the record, but I know that theta equals a third has been proved, and maybe something very close to a third is the record at the moment. So trying to beat that error term, you can see things get more and more complicated. Actually, it's the best improvements on the error term of this particular problem use sophisticated algebraic geometry. So there are some interesting connections to geometry and things like that. All right. Now that's just the general nature of number theory, that you just don't know what the problem is about. Even though you may understand the problem, you just don't know what the problem is about. You can state it simply and you still don't know what the problem is about. Here's an example of case in point. Suppose f of x is an irreducible polynomial. And for each prime p, let rho sub f of p equal the number of solutions of the congruence f of x is 0 mod p. So for each prime p, we're going to let rho of p be the number of solutions mod p. Now, as you know from your basic algebra, the number of solutions of a congruence mod p for a polynomial of degree d is at most d, because over any field, the number of roots of any polynomial is at most the degree of the polynomial. So we know rho sub f of p is always bounded by the degree of f. My question now is there an asymptotic formula for summation p less than x rho sub f of p. In other words, I'd like to know how does this function behave, at least as a summatory function. Now, let me just give you a quick example of perhaps the kind of thing we will be up against. Example. I mean, you know, when I ask you a question like this, just off the top of my head, sometimes it's not clear exactly what does this entail? What is this question? So I keep telling you, in number theory especially, more than anything else, you can ask a question that high school kids can understand, but exactly what does it involve is another matter altogether. This is our case in point. Let's just look at it. Let's look at the following example. F of x equals x squared plus 1. Okay? So when can I solve this congruence mod p? Now, some of you may know the answer already. So those of you who know the answer, what is it? If and only if it's congruent to 1 mod 4. Yeah. So the answer is, as she says, if and only if p is congruent to 1 mod 4. What about p equals 2? Got you. Okay? This is only for odd primes, okay? So this answer is correct in the case of odd primes. For p equals 2, of course, x equals 1. It's a double root, right? And p equals 2, we have a double root. So this is the answer. And how would you prove this? Any ideas? What is it? Using what? Yeah, but why do you want to go that far? I want to do it with bare hands. First, let's try to show that if p is congruent to 3 mod 4, I mean, according to this answer, there's no solution, right? So let's try and show no solution. How do we do that? So suppose not. It's a good way to begin, right? Suppose not. So we have x squared congruent to minus 1 mod p. We have a solution. And we have what's called Fermat's little theorem. That's FLT. Okay? Maybe there should be a little L. Which says that a to the power p minus 1 is congruent to 1 mod p all the time, right? That's what it says. So let's raise both sides of this thing to the power p minus 1 over 2. Right? Now p is congruent to 3 mod 4, so it looks like 4k plus 3. When I subtract 1, that's 4k plus 2. Divide by 2, that's 2k plus 1. That's an odd number. So this is congruent to minus 1 mod p, exactly. But Fermat's little theorem tells me the left-hand side is congruent to plus 1 mod p. Therefore, I have a contradiction. Right? In this little case, p congruent to 3 mod 4, there's no solution. I just use Fermat's little theorem. Fair enough? So at least that, so if there is a solution, p has to be congruent to 1 mod 4. Or p is 2, of course. 2 by, you can do it by inspection, right? All right. Let's do p congruent to 1 mod 4. Let's try and show that there is a solution. Can we show there is a solution? You know, without using any fancy things, right? So, any thoughts on this one? Does Wilson's theorem ring a bell? If you take a prime p, you multiply 1 to up to p minus 1, that's p minus 1 factorial. It's always congruent to, exactly, minus 1 mod p. And how do you prove that? Exactly, you can prove pairs of inverses. So x and x inverse get paired and they multiply to give 1. The only one problem is there may not be a pair. When is there not a pair? When x and x inverse are the same. In other words, x squared is 1. That can happen if x is plus 1 or minus 1. In those two cases, there are no pairs. So in that, the thing that left over is minus 1. Okay? Now this actually can be used to demonstrate that this congruence that we have has a solution. So we can write this as 1, 2, up to p minus 1 over 2. Okay? And then the next one is p minus 1 over 2 plus 1. Okay? The next one is p minus 1 over 2 plus 2 dot dot dot. And p minus 1 over 2 plus p minus 1 over 2. Okay, is this fair enough? So this is what I wrote down. Now this guy here is p plus 1 over 2 and can be thought of as p minus 1 over 2. Is that right? Look okay? So this can be thought of as p minus 1 over 2 minus 1. Everybody okay with that? Dot, dot, dot. This is p minus 1, so this is p minus 1. Okay? So in other words, what I'm saying is, if p is going to be 0 mod p, right? That's just, so I've got minus of this, minus of this, minus of everything, right? So this is essentially, there's a minus sign for how many times? Well, p minus 1 over 2 times. And I've got p minus 1 over 2 factorial squared. Right? And all of this is congruent to minus 1 mod p, right? P is now, in our case, 4k plus 1, congruent to 1 mod 4, right? 4k plus 1 minus 1 is 4k, divided by 2 is 2k, so that's an even number, right? And therefore, I have solved the congruence x squared congruent to minus 1 mod p. I've actually even given you a solution. Okay, so this is the proof of this fact. You really don't need anything except bare hands. Fermat's little theorem, and Fermat's little theorem and Wilson's theorem are more or less the same. Okay, so you can kind of think about that. So we can already see that in the simplest of cases, this innocent-looking problem of counting solutions in this particular example is asking me for what? Well, it's 0 if p is congruent to 3 mod 4, and 2 rather, if it's congruent to 1 mod 4, and 1 solution if p equals 2. Therefore, in this special case, our problem, let's say it here, in the special case, so this is if and only if p is congruent to 1 mod 4, in which case rho sub f of p is 2. If p equals 2, rho sub f of p is 1. And if p is congruent to 3 mod 4, it's 0. So my problem of counting these solutions is really the number of primes up to x congruent to 1 mod 4 plus 1 because of the p equals 2 case. To find an asymptotic formula for this is tantamount to, sorry, there's 2 times that, right? Is tantamount to calculating the number of primes congruent to 1 mod 4. But we did that. That was a special case of Dirichlets' theorem. We know that that's asymptotic to 2 times pi of x over phi of 4. Phi of 4 is 2. So this is asymptotic to pi of x. Okay, so this is, but we're basically, you needed to know something about the asymptotic behavior of primes. You needed to know this counting function. I don't see how to solve this problem without knowing this. This is completely equivalent to that special case of Dirichlets' theorem. Now we know that how hard, what a tough time Dirichlet had in trying to prove his theorem. So such an innocent-looking problem all of a sudden translates into something non-trivial, and so it shouldn't be a surprise that this is really opens the door to algebraic number theory. That's what it is. This is really a problem in algebraic number theory. You would never guess it. All right, so is it fair enough? Now, I'd like to show you how you would use the Tauberian theorem and algebraic number theory somehow to solve this problem in general. And as you can see, it's a generalization of Dirichlets' theorem in some sense. Okay. So this question is really question in algebraic number theorem. Well, as he says, I mean, in the example, the toy example I started with, it really is something about the arithmetic of the Gaussian integers. That's true. So something is going on. In that case, we were, you know, could do it with bare hands, but in general, you'd have to get your hands dirty a little bit. So. So here's a crash course in algebraic number theory. So K is an algebraic number field. Means it's a finite extension of the rationals. Okay. Inside this field, there's a collection of elements. Alpha satisfies a monic polynomial with integer coefficients. So all the collection of elements in capital K that satisfy, that are the roots of a monic polynomial equation with integer coefficients, you look at that totality, and it's a beautiful theorem of Dedekind that this set is actually a ring. So Dedekind showed OK is a ring. That's a nice theorem. And this ring is called the ring of integers of K. We call this ring the ring of integers of K. Now, Dedekind and many others at the time were motivated to study these rings, actually in their attempt to prove solve Fermat's last theorem. So, as I've often said, major unsolved problems are kind of stepping stones to make major discoveries. The problem by itself perhaps may be unimportant, but you are led to make fundamental discoveries like these beautiful objects, structures of these rings, and so on and so forth. So another important thing that Dedekind proved is the analog of unique factorization of natural numbers. He showed that every ideal in this ring can be factored as a product of prime ideals uniquely. So O sub k, he showed further that every ideal, every non-zero ideal of O sub k can be written as a product of prime ideals uniquely. This is the analog of the unique factorization theorem for natural numbers. Okay, so you can factor all the ideals uniquely, and inspired by the Riemann zeta function, he well, it turns he tried to define a zeta function, so here's how it goes. It turns out that this particular ring has the property that for every ideal A of the ring, the index of the ideal is finite. Turns out it's finite. Index is finite. Every non-zero ideal, sorry. For every non-zero ideal, it's finite. And therefore, we can define, he defined norm, he defines the norm of an ideal to be this index. Okay? The norm of this ideal is the index. And he shows that the norm is a multiplicative function on ideals. That is, norm of A times B is equal to norm A times norm B. Therefore, it's a multiplicative function. Therefore, he defines the Dedekind zeta function. Well, he didn't call it the Dedekind zeta function. We do now. Call it the zeta function of the number field. One over the norm A to the power S, where I'm running over all the integral ideals which are not zero. And because every ideal can be factored as a product of prime ideals uniquely, just like in the Riemann zeta function case, I can write it as an infinite product over okay, and he managed to show that this thing converges for real part S bigger than 1. It's not difficult to show. And he asked the obvious question, just like the prime number theorem is about counting the number of primes up to x. He wanted to know how many prime ideals are there whose norm is less than x. So the analog of the prime number theorem he was making a guess. Let pi sub k of x be the number of prime ideals if you want to be a number theorist, you should learn how to make German calligraphic symbols, okay? Very important. The German P. Okay. To practice your calligraphy. Anyway, so you want to count the number of prime ideals whose norm is less than x, and I believe he was guessing this. Is this true? Okay. Now, it should not come as a surprise, especially because I have been dancing around this particular statement and not erasing it. This statement is the same as this, turns out. It's completely equivalent, just like in the case of that toy example, x squared plus 1 I gave you. all of a sudden leading to counting primes congruent to 1 mod 4. In fact, if the answer to this is this, the answer to this is also x over log x. It's completely equivalent. You would never guess it. So this is the beauty of number theory. This is why I do number theory. It's so fascinating that, you know, firstly it's like, you know, these sirens, in Greek mythology, you know, these sirens, they attract these sailors or so, you know, with their singing, right? These elementary problems kind of seduce you into paying attention and trying to study them, and then you're hooked, right? So it's something like that. But it's better than that. Usually those sailors got killed. We don't get killed. Okay? People who do number theory are rewarded. So there are rewards. So maybe that's a bad example. Maybe it's more like Krishna and his flute is a better example. Okay, so that's the problem. Now, how would you connect these two to the this question? Well, it has to do with, again, Dedekind's fundamental researches. So so here I have told you that O sub k is a ring, and given a prime p, we may consider the ideal generated by p. The principal ideal in that ring, we consider the ideal generated by p. Okay. Now that's a perfectly good ideal. Dedekind's theorem tells me every ideal can be factored as a product of prime ideals uniquely. So these PIs are prime ideals. Distinct prime ideals, right? We have this unique factorization of ideals in this ring. And the question is, abstract theory is fine and dandy, but how do I get my hands on those ideals? How do you give me those ideals? Okay. So Dedekind came up with a recipe. So my first step is to show you that these two are equivalent. I just told you that, but didn't show it to you, okay? I have to show it to you. Now I have to do it through this theorem. So Dedekind's recipe is the following. So now every number field by the theorem of the primitive element can be written as Q of theta for some theta, right? So the theorem of the primitive element tells you that Q is some Q of theta, where theta is some algebraic number, and minimal polynomial, algebraic integer actually, minimal polynomial, let's say, is f of x with integer coefficients. So suppose I can now tell you my field looks like Q of theta, where theta is a root of some irreducible polynomial f of x. The minimal polynomials are irreducible, of course, you know that, right? So f of x is irreducible, you have that. Then here's how Dedekind gives you a recipe for finding those prime ideals P. So he says, take your polynomial f of x now that you have it in your hand, and factor it mod p, that is over the polynomial ring fp of x. You can, fp is a field, fp of x is a polynomial ring over a field. It's a Euclidean domain, therefore you can factor it as a product of prime irreducible polynomials. So factor it I deliberately use the same symbols. Okay, so factor it as a product of irreducible polynomials. Then, having done so, look at the ideal p sub I generated by the number p and this polynomial fi of theta. This is an ideal. This is an ideal sitting inside O sub k. Then Dedekind's recipe is, apart from finitely many primes p, so there's some finitely many primes p which you just have to throw out from the discussion. Having done so, then the ideal generated by POK is precisely P1 to the E1, P sub R to the E sub R. So in other words, if I throw away these, special primes, these primes are called primes that might divide the discriminant, which we'll not talk about, okay? If we throw those finitely many primes away, there's a kind of a one-to-one correspondence between the factorization of f of x mod p and the factorization of the ideal generated by p in that field. That's an amazing theorem. Very impressive, very, very impressive theorem. So that, who would have guessed it? Factoring a polynomial mod p is really factoring ideals in some number field like this. So now you can see immediately what it means for us to be able to solve the congruence mod p. Oh, there's one more point that I should tell you. I should tell you that the norm of the ideal pi is p to the degree of fi. I mean, this functoriality is so neat. The norm of these prime ideals is p to the power degree of fi. So to say that f of x is 0 mod p means that, to say that it has a solution, means that when I factor it, there's a linear factor here. That means there's a polynomial fi of degree 1, which means that there's a pi in here whose norm is p. And every time there's a polynomial, every time there's a prime ideal of norm p, there was a root there. So the number of roots here is equal to the number of prime ideals in the field whose norm is p. Very interesting. Therefore, it is not going to be a surprise now to see that this counting thing is really counting the prime ideals whose actually norm is p. Remember, prime ideals whose norm is p squared and higher contribute less to the sum. So those, we don't need to worry about those, okay? So I think from this, understanding this theorem allows you to establish an equivalence between this and this. They're completely equivalent in this sense, as terms of asymptotics. Everybody happy with this? Okay. So now we have a Tauberian machine which tells us how do you go about getting these asymptotic formulas. In other words, this is nothing but the so-called prime ideal theorem. So it's not a prime number theorem, it's the prime ideal theorem. That is, how many prime ideals are there whose norm is less than x. That's what's called the prime ideal theorem in number theory. So how do you count that? Well, I have this factorization. We need an analytic continuation greater than or equal to 1. Except for a simple pole okay, so this, now that you understand it, so this was a thesis problem for Heinrich Weber, who was Dedekind's student. He solved it. What he did was he actually counted the number of integral ideals up to x. So Weber counted the number of ideals with norm less than or equal to x. It turns out to be a lattice point counting problem. Not trivial, but once you formulate it as a lattice point. He counted that. He ended up by showing that this was equal to some residue of some number, rho sub k, which I will not go into, plus O of x to the 1 minus 1 over the degree. D is the degree of the field. Now you guys all know about partial summation. So if I know the number of ideals of OK up to norm less than x, here, what is this? I can rewrite this as summation an over n to the s. After all, this is just an ordinary Dirichlet series, although it was constructed rather exotically. It's really a Dirichlet series again. A sub n over n to the s. What is A sub n? A sub n is the number of ideals whose norm is n. So summation n less than x is exactly this. Once you have this, you can use your partial summation lemma to show that the Dedekind zeta function has an analytic continuation up to real part s bigger than 1 minus 1 over d with a simple pole at s equals 1 and residue equal to rho sub k. Okay? So at least you now get the Dedekind zeta function analytically continued to the region at least real part s bigger than or equal to 1. Now the question is, before you apply the Tauberian theorem, you remember you have to have, what do we want to apply the Tauberian theorem to? Well, we want to apply it to zeta k prime over zeta k of s, right? Zeta k of s over zeta k of s is equal to, when you look at it, the usual logarithmic derivative, you'll have an analog of the von Mangold function, right? The von Mangold function is going to be equal to log of norm p if a is a power of a prime ideal and 0 otherwise. Usual extension of the von Mangold function, okay? Having done so, oops, there's a minus sign here. Having done so, what we really want is we want to calculate that. The Tauberian theorem tells you that if you have this Dirichlet series, it has analytic continuation to real part s bigger than or equal to 1. Well, we have it now. We continued zeta k of s up to 1 minus 1 over d. And therefore, this has a nice meromorphic continuation in that region. The only problem is this silly thing can be 0 again on the line 1. So we need to know zeta k of s is not 0 for real part s equal to 1. But the proof that that doesn't vanish, you know, is the same as the proof that we gave for the Riemann zeta function case. Because remember, we exploited the Euler product. Everything is, all the coefficients are non-negative. Therefore, the proof goes through mutatis mutandis, whatever that means. Okay. Mutatis mutandis is Latin to say that without any change. Sounds good, so I used it. Anyway, so this proof of the fact that this doesn't vanish is the same as before. Simple pole at s equals 1. Therefore, this is asymptotic to x by the Tauberian theorem. And therefore, you can do your partial summation business and get this. And then you've solved the problem of counting solutions of a polynomial congruence mod p using the theory of the Dedekind zeta function. There is, as far as I know, there is no other way that you can do this. Maybe since I've run out of time, I'll stop here. So next time, which is I guess tomorrow and Wednesday, I will continue this kind of framework of thought and describe a more general equidistribution theorem. So here now we have a theorem about distribution of prime ideals. So in general, is there some general framework? Anytime I have a question about equidistribution, can I bring in the theory of L functions or zeta functions into the picture and solve it just by invoking the Tauberian theorem? The answer is sometimes you can. Sometimes you cannot. And I want to talk about when you can, when you cannot, and explain how these things work tomorrow and day after. Yeah? Okay.